A team of researchers at Utrecht University in the Netherlands just published a paper that forced oceanographers around the world to stop what they were doing and pay attention. The study, led by René van Westen and Henk Dijkstra, appeared in Communications Earth and Environment in early 2026, one of the most respected journals in climate science. What they found, using a high-resolution ocean simulation that most climate models aren't capable of running, is that the Gulf Stream, the massive ocean current that flows right past Florida's coast, is drifting northward. And it's not just drifting. Their model shows that before the Atlantic's entire circulation system collapses, the Gulf Stream doesn't gradually fade. It jumps 136 miles northward in 2 years. And when they checked satellite altimetry data from 1993 to 2024, they found a statistically significant northward trend already underway. Right now. Off Cape Hatteras, the real-world ocean is doing what their collapse model predicted it would do in the early stages. Let me explain what that means for Florida, and why the sun top. Satellite data showing changes along the Atlantic coast is about something much bigger than beach erosion. First, you need to understand that sea level isn't flat. I know that sounds strange, but it's one of the most important things to grasp about how oceans actually work. The surface of the Atlantic right now, at this very moment, isn't a uniform sheet of water at the same height everywhere. It's lumpy. It's shaped by currents, temperature differences, salinity, wind patterns, atmospheric pressure, and even the gravitational pull of nearby land masses and ice sheets. The difference in sea surface height between one side of the Gulf Stream and the other can be more than a meter. That's not a typo. There can be over 3 feet of height difference across a single ocean current. And that's because of something called the Coriolis effect. The rotation of the Earth deflects moving water to the right in the northern hemisphere, which pushes the Gulf Stream's flow away from the US coast and piles water up on the offshore side. Here's where it gets serious. When the Gulf Stream weakens or shifts position, that offshore push relaxes. And when it relaxes, water sloshes back toward the coast. Multiple studies, from researchers at the Potsdam Institute, NOAA, the University of Miami, and Virginia Tech, have projected that a significant weakening of the Atlantic Meridional Overturning Circulation, or AMOC, could raise sea levels along the US East Coast by an additional 15 to 20 centimeters by 2100. That's 6 to 8 inches on top of all the other factors already driving sea level rise. And if the AMOC were to substantially weaken before that? Some models project a rapid rise of 8 to 12 inches along the southeastern United States, concentrated right along Florida's Atlantic coast. So when satellites capture anomalous behavior along Florida's shoreline, temporary retreats, unusual tidal patterns, exposed shelf areas during certain weather windows, those aren't just quirky coastal events. They're data points in a much larger story about how the Atlantic Ocean's circulation is changing. Now let me take you through that larger story, because the AMOC is the engine behind all of this. Picture a giant conveyor belt that stretches the entire length of the Atlantic Ocean. Warm surface water flows northward from the tropics, past Florida as the Gulf Stream, up past the eastern seaboard, across to northern Europe. Along the way, it releases heat into the atmosphere, which is why Western Europe is so much warmer than it should be for its latitude. London is as far north as Calgary, Canada, but doesn't experience Calgary winters. That's the AMOC at work. When that warm water reaches the high North Atlantic, it cools, becomes denser, sinks to great depths, and flows back south along the ocean floor. It's a cycle that moves roughly a quadrillion watts of heat northward. And right now, that cycle is showing signs of weakening. The evidence is stacking up from multiple independent lines of research. In the North Atlantic, south of Greenland, there's a region that's actually been cooling while the rest of the ocean warms. Scientists call it the cold blob, and it's been identified as a fingerprint of reduced AMOC heat transport. A 2025 high-resolution ocean model from Van Westen's group at Utrecht showed that when you simulate an AMOC shutdown, the sea surface temperature pattern, you get the cold blob in the North Atlantic. The Gulf Stream shifting northward matches what satellite observations have actually recorded between 1993 and 2021. That's not a prediction anymore. It's a pattern match between theory and reality. The Gulf Stream itself has shifted roughly 10 kilometers closer to the US shore since the early 2000s, according to three-dimensional observations collected by Argo profiling floats, a fleet of nearly 4,000 autonomous instruments scattered across the world's oceans. Separate research using the Rapid Monitoring Array, a line of sensors stretching across the Atlantic at 26.5 degrees north, has measured the AMOC's strength directly since 2004. The data shows variability, but the trend is downward. Now, there's an important nuance I need to address. A 2024 study from NOAA's Atlantic Oceanographic and Meteorological Laboratory, led by Denis Volkov, found that the Florida Current, the specific branch of the Gulf Stream that flows through the Florida Straits, has actually remained remarkably stable over the past 40 years of direct measurement. Earlier claims of a significant decline turned out to be based on uncorrected data from a submarine cable used to measure the current's transport. Once corrected, the negative trend in the Florida Current shrank substantially and became only marginally significant statistically. Volkov was clear about what this means. If the AMOC is weakening, it hasn't yet shown up clearly in the Florida Current. But he also said the observation record may simply be too short to detect it with confidence. This is exactly the kind of complexity that gets lost in headlines. The ocean doesn't change in a straight line. The AMOC doesn't weaken uniformly across all its components at once. The Gulf Stream can remain stable in one segment while shifting in another. And satellite data can capture short-term anomalies, coastal water pulling back. During certain wind events, tidal irregularities, temporary exposures, that look dramatic but may or may not be connected to the longer-term circulation changes. The science is about separating signal from noise, and that requires decades of consistent measurement, but the signal is getting harder to ignore. In October 2024, 44 Furdan, leading climate scientists published an open letter warning that the risk of AMO collapse has been vastly underestimated by previous assessments. The IPCC's most recent evaluation expressed only medium confidence that the AMOC wouldn't collapse before 2100. But a growing body of research suggests that confidence level may be too optimistic. Danish researchers Peter and Suzanne Ditlevsen published a statistical analysis in Nature Communications, projecting that an AMOC collapse could occur most likely around 2065, with 95% confidence that it would happen somewhere between 2037 and 2109. That study drew criticism. It relied on intermediate complexity models and proxy temperature data that many scientists consider insufficient. But it also shifted the conversation. The timeline tightened. And in 2025, a multi-model analysis that extended climate simulations beyond 2100 found that under high-emission scenarios, the deep northern overturning cell of the AMOC, the engine room of the conveyor belt, weakened dramatically in every single model that was run. Every one. The question wasn't whether it weakened, but how fast. So what would this actually mean for Florida? Let me lay out the cascading consequences. If the AMOC weakens significantly, sea levels along Florida's Atlantic coast rise faster than the global average, potentially 6 to 12 additional inches from the circulation change alone. Coastal flooding events that currently happen a few times a year could become monthly. Storm surge from hurricanes pushes further inland because it's starting from a higher baseline. The 432 miles of Florida's coastline, already classified as critically eroded, lose sand faster as wave patterns shift. Saltwater intrudes further into the freshwater aquifers that millions of Floridians depend on for drinking water. And the marine ecosystems, coral reefs, mangroves, seagrass beds, fisheries, get squeezed between warming water temperatures above and changing current patterns below. For the roughly 16 million people living along Florida's Atlantic coast, and for the coastal real estate market valued at hundreds of billions of dollars, this isn't abstract. Insurance premiums, already brutal in Florida, averaging $3,500 to $8,000 a year for property coverage, would face even more upward pressure as flood risk models incorporate AMOC-related sea level projections. Now, some of you are thinking, didn't you just Say the Florida current has been stable for 40 years? Isn't this contradictory? And that's exactly the right question. The answer is that climate systems operate on multiple timescales simultaneously. The Florida current can be stable over 4 decades, while the broader AMOC shows a weakening trend over a century. Short-term measurements and long-term dynamics can tell different stories that are both true. That's why scientists like Volkov are careful to say the record isn't long enough yet. Not that there's nothing to worry about. The Van Westen simulation showed that the Gulf Stream's gradual northward drift lasted 392 simulated years before the abrupt jump. We might be in the gradual phase, right? Now, the satellite data is consistent with that interpretation, but we won't know for certain until the record gets longer, or until the jump happens. So what's being done? 3 things matter. First, observational networks. The Rapid Array, the Argo float system, satellite altimetry missions like Sentinel-6 Michael Fries, and NOAA's tide gauge stations along Florida's coast. These are the instruments that will detect acceleration if it comes. Maintaining and expanding them isn't optional. It's the early warning system. Second, climate modeling at higher resolution. Van Westen's work was groundbreaking precisely because it used a model fine-grained enough to capture Gulf Stream dynamics that standard climate models smooth out. More computing power applied to this problem means better predictions. Third, coastal adaptation. Florida needs to plan for scenarios where sea level rise along its Atlantic coast outpaces global averages. Stormwater infrastructure, building codes, insurance frameworks, and managed retreat discussions all need to incorporate AMOC-related projections, not just global mean estimates. If you're in Florida, or anywhere along the US East Coast, here's the practical takeaway. The Atlantic isn't just rising, it's reorganizing. The currents that shape your coastline, your weather, your flood risk, and your water supply are part of a system that's under stress. The satellites are watching. The instruments are measuring. And what they're capturing right now is the opening chapter of a story that will define coastal life for the rest of this century. I'll be following this story as it develops. The AMOC data, the Gulf Stream tracking, the Florida coast impacts. In the next video, I'm going to break down what the latest climate models predict for the Atlantic over the next 30 years, and why the projections have shifted so dramatically in just the last 2 years. Make sure you're subscribed so you catch that when it drops. I'll see you there.